looking at Chapter 11, Section 3. We're going to cover the last major gas law, which is the ideal gas law. Starting off with Avogadro's principle. This one is looking at volume and moles of a gas. And for moles of gas, we are going to use the letter N. We're going to use the letter N. So when you divide these two variables, volume and moles, you get a constant value, which means they are directly related. So now if we take the gas law, the combined gas law, and we add Avogadro's principle to that, we can develop the ideal gas law. So again, we're going to merge the combined gas law with Avogadro's principle, and we get PV over NT equals K, which is a constant. So pressure times volume divided by moles and temperature. Again, temperature has to be in Kelvin. You get a constant. This constant has a special name. It is R, and it is the universal gas constant. There are two values of R that I want you to be familiar with. They are listed right here. And notice that the set of units is going to be a little bit different. I'm going to rewrite these just so that you can see them side by side too. So here are those two different universal gas constants or values for R. And when I'm looking at this, I want you to see that both of them use moles, both use Kelvin. And if I look at the volume part of this, the liters and the decimeter cubed, those are actually equal to each other. One's an SI unit, the other's non-SI, and 1 decimeter cubed does equal 1 liter. So technically those parts are interchangeable too, along with your mole and Kelvin. And then that leaves us with our pressure unit, atmosphere and kPa. You know that they are not equal to each other. So that is the true reason for the difference in the two numbers that you see here. So again, this is taking a volume unit, which is liters or decimeters cubed, times a pressure unit, that's your atmospheres or kilopascals, dividing by moles. We're using the letter N to represent moles. And then Kelvin is a temperature unit on the bottom. So Vp over NT does equal a constant value R. And these are the two values of R that we are looking at. We rewrite this to get everything in a numerator as PV equals nRT. So the N and the T have been taken out of the denominator and put over there with the R value. This equation is the major equation that I want you to know for the ideal gas law, PV equals nRT. Now when I look at this and I compare it to the combined gas law, which we're going to go do that now, as I compare these, notice some major differences in it. Here's the number one major difference. N, which is our moles. At no point in the combined gas law is moles ever listed. If you have mass listed at any point within your problem, mass, we know we can do a mass to mole conversion by setting up a grid. So mass to mole, there's the molar mass of the compound. You get this number from the periodic table, and this is going to be some value that is probably given. So again, if you see mass or moles listed in your problem, that's automatically at some point going to deal with the little n, which your combined gas law doesn't have. Also, too, in the combined gas law, we have two sets of data. You might have two pressures listed, or two volumes listed, or two temperatures listed. Whereas the ideal gas law, you're only going to have one set of data actually listed per pressure, volume, and or temperature. So write out this problem and let's go try to solve it. It says calculate the pressure. So again, calculate the pressure in atmospheres, so it does want it in atmospheres, of 0.412 moles, that's my value of N, of helium, so I know I'm dealing with helium, at 16 degrees Celsius. Well, there's my temperature that will have to be put in Kelvin. Occupying 3.25 liters. I know liters is a volume unit. It is a volume unit. So if we go assign our different variables or symbols to each of these, we get pressure is what we're looking for in atmospheres. 0.412 moles, we're using the letter N. Temperature, we've converted that to Kelvin. Volume is in liters, and the R value that is being used is this one right here, and it's based on the units. So if I look at the units, this R value uses liters, which is great because my volume given was in liters. It's using Kelvin. That's great because my temperature I know has to be in Kelvin. We also have moles. Yep, moles was given, and it wants us to solve for our pressure in the units of atmospheres, and this does use atmospheres. So that R value has the correct units needed so that eventually most of them cancel out except for the atmospheres because we want that in our answer. So if we go in and we plug everything into PV equals nRT, pressure again is what we're solving for. Volume was 3.25 liters. N is 0.412 moles. I know I'm going to write it like this because it's going to get tight. The R value we said is 0.0821, and that is liter atmosphere over mole Kelvin. And then our temperature is 289 Kelvin. 289 Kelvin. When I bring my 3.25 liters over to divide, because we've got to get rid of it on that side, and get pressure all by itself, I can see that some things that are going to cancel here, liters and liters. This Kelvin's really in the numerator, that one's in the denominator. This mole is in the numerator, this one's in the denominator, so those are going to cancel, and I am left with atmospheres in the numerator. So when you solve for this, you're going to get 3.01 atmospheres. So make sure you can put all of this into your calculator properly. And the last example we're going to look at says find the volume of 85 grams of oxygen at 25 degrees Celsius and 104.5 kPa. So we're going to be looking for volume. 25 degrees Celsius, well, that's the temperature we're going to use, but in Kelvin. And kPa is a pressure unit. Notice earlier I said if you're given mass, that's going to have to be converted. So that 85 grams of oxygen must be converted to moles. So grams to moles. And again, that was understood per 1 mole. I'm going to look at the periodic table. I know I have 2 oxygens, and each of those from the periodic table has a mass of 16 grams, which is 32. So I'm going to plug in my 32 right here and solve. I've been using the proper significant figures through all of this. So when I do that, this will give me 2.7 moles. Now I can plug that in as my value for N. My value for N, 2.7 moles. Let's go ahead and pick our R value. If I had to pick an R value that I was going to work with, I need an R value that has kilopascals, moles, Kelvin, because 25 degrees Celsius in Kelvin is 298 Kelvin, so I need Kelvin. And it says find volume, but it doesn't tell me what the volume units have to be. Well, my only R value that has mole Kelvin and kilopascals is that one that was 8.315, and that was decimeter cubed kPa over mole Kelvin. So it looks like my volume unit is going to be in decimeters cubed, which we said is also equal to liters. So there's our information given. Going to this already shows you the math, trying to get the N switched over to moles, so we did have to do grams to moles. PV equals nRT, plug everything in. To get volume all by itself down here, you do have to take this number and divide it on both sides. So in your calculator, it'd be 2.7 times 8.315 times 298 divided by 104.5 kilopascals. And you can see your units cancel out here. kPa cancels, mole cancels, Kelvin cancels. We are left with decimeter cubed. And your final answer is 64 decimeters cubed, which is also equal to 64 liters.